All right. So where did we leave off last time? We did quite a lot last time, didn't we? We were looking at singularities. So there's removable singularities. I guess we proved one theorem about each. Removable singularities. We proved the Riemann removability theorem. Riemann f bounded near z0 implies removable. Then we proved the pole theorem. Absolute value of f goes to infinity if and only if pole. And then we proved a essential singularity theorem, Casorati-Weierstrass. Casorati-Weierstrass. Well, how shall I say this? If z0 is an essential singularity, then for every little disk around z0, the image of f, well, I can't evaluate it at z0, but I can evaluate it otherwise, will approach every complex number, right? And then we looked at the extended complex plane, showed how it can be realized as a Riemann sphere, and we showed that any function that's meromorphic in the entire complex plane, including infinity, either approaching a limit at infinity or blowing up at infinity. And we know that being bounded is sufficient to approaching a limit. Then on C infinity implies rational. Is that where we stopped? No, we did the argument principle. We did the argument principle. We're chugging along right along. The argument principle. Let's have an argument about a principle. Which says that if f is meromorphic on some region R contained in an open domain, and f has no zeros or poles on the boundary of R, which is a toy contour, then the integral over the boundary of f prime over f, the logarithmic derivative, counts with multiplicity, a +1 for every 0 and a -1 for every pole. We did this, right? Yeah, great. Okay. All right, let's get some applications.
Do you need a modulo 2 pi I somewhere or no?
Thanks. As usual, 2 equals pi equals I equals 1. Yes. This integral is misdefined. It should be defined with a 1 over 2 pi I as part of the definition. All right. We proved the argument principle. Let's get there's some fantastic, I'm like a broken record, right? Here's some fantastic application that we don't have a right to know. Rouche's theorem. Here's a crazy theorem. Suppose f and g on some region are both holomorphic, and let's do it on a disk. I don't know, it doesn't matter. Let's do it on a disk. And there's a disk whose closure is inside omega. And on the boundary of the disk, the absolute value of f strictly exceeds the absolute value of g. Okay? In other words, if we have a graph, so here's the complex plane, here's a disk, D, on the circle, f looks like this, and g, whatever g is doing, is strictly below f. But I have no idea what's going on inside. Then, the number of zeros of f, inside D is equal to the number of zeros of f plus g inside D. So if I take F, which I'm thinking of as this upper surface, and I add G to it, there's no way to create more zeros. All I know, so there's certainly no way to create more zeros on the boundary. I said F is bigger than G. You add F and G, you can't get a zero on the boundary. But why can't you get extra zeros in the interior? Who's to say that this can't happen where they cross, and so their sum, right? I'm not showing you what the sign is. F could be positive and G could be negative. And so that the place where they cross, they exactly cancel and create a new zero. Why can't that happen? Okay, so this picture does not exist. It's kind of crazy. Why is this true? Well, if we only had some way to figure out what the number of zeros of F inside D was. Okay, everybody sees the argument principle. Let's not forget the 1 over 2 pi I over the circle F prime over F. So make a new function, and of course the same is true for F plus G. So for T, we're beginning to think about deformations and homotopy. We're about to get into the discussion of homotopy. For T in the unit interval, let F sub T of Z be defined as F of Z plus T times G of Z. Okay, it's not T of, it's just T times. This function is, I mean, F and G are holomorphic. They're not only continuous. T is, I mean, this is some linear combination. This function is jointly continuous in Z comma T in omega cross 0, 1. You understand what I mean by that? I take the pre-image of an open set, I get an open set. Right? If I only wiggle, if I want to wiggle the value of F sub T just a little bit, all I have to do is wiggle Z and T a little bit. Okay. Then, well, one thing we know is that F of T of Z restricted to this circle never vanishes. Why?
Strictly greater than the absolute value of G.
Exactly. Since F is strictly greater than G on C. That's all I know. On the boundary, F is strictly greater than G. And so this sum can't possibly, the smallest this sum can get is absolute value of F minus absolute value of G. That's strictly positive on C. Okay, that means I can apply the argument principle. Then 1 over 2 pi I integral over C of ft prime over ft dz is the number of zeros of ft inside the disk D. I can take this integral precisely because the denominator never vanishes. That was a necessary condition in the argument principle, wherever it is. We need to know that F has no zeros or poles on the boundary so that this makes sense. Now this is a jointly continuous function. I'm dividing by a non-zero value. In fact, if we're looking at the closed disk, so if we look on the closed disk cross 0, 1, which is compact, ft is uniformly away, stays uniformly away from 0. So this denominator really doesn't do anything funny, right? I mean, you can think about it either on the closed disk or just on the circle. The circle cross 0, 1 is also compact. And so, so you never really get near zero. Sorry, f might vanish. This is wrong. This is wrong. F might vanish inside, but it certainly doesn't vanish on the circle, and the circle is compact. I really do want to use the circle. And that's supposed to be a cross. Looks more like a... Okay, so on the circle in Z, cross 0, 1 in T, f stays uniformly bounded away from 0. And so this integral, let's call this I sub t, therefore I sub t is a continuous function of t. This is varying continuously. This doesn't have a chance of blowing up. Everything is nice. You're integrating over a compact region, a function that stays some fixed distance away from 0. And so as a function of t, this is a beautiful continuous function of t. And what's the problem?
We can only take on integral values.
This is an integer. This is an integer. So a continuous function on the integers is flat. The only way to be continuous on the integers, but it is z valued, hence constant. And its value, and I sub 0, is exactly the number of zeros in f of f in D, number of zeros of f inside D, which has to equal I1, which is the number of zeros of f plus g in D. Does that make sense? So you can't, there's no way to get this picture to happen where where on the boundary there's room, but as surfaces they intersect. If they intersect, then you multiply g by whatever complex number of absolute value 1 you need so that this difference is exactly 0. You see what I mean by that? If this color is red, meaning the argument is that way, what is it? Red. But what was our color scheme? Roy G. Biv. Red, orange, yellow, green, blue, violet, indigo, something like that. Indigo, violet. So if it's pointing, if f is pointing red, multiply g by a complex number of absolute value 1, which doesn't change the absolute value on anywhere, including on the boundary. So it doesn't change the condition about the boundary. You'll create a 0. So this picture doesn't ever happen for complex analytic functions, for holomorphic functions. Okay, so what? Well, now we're going to get some crazy consequences. I mean, this itself is kind of a crazy theorem. Any questions on Rouche? Make sense? Anna, it's good? Theorem, good? Okay. All right. Let's prove another fantastic theorem. So over R, you can have analytic functions. F can be analytic and look like this. Let's say open 1, 2, 3. The graph of F is something like this. And so the image, maybe this is 2, and maybe this is 4. The fact that if F is continuous is equivalent, just as it is over the complex numbers, to the fact that the pre-image of open sets is open. Right? We've talked about this before. Why this is true topologically. Why it's equivalent to your epsilon delta version. Tell me if not. Have we talked about this or no? Thomas?
Sorry, I'm still thinking about something with Rouche. I'm trying to.
Oh.
Why am I think I'm missing something, but it feels like it should be. What was the picture you were drawing that was like, oh, what could happen? Because it feels like it should be immediate. That like adding G to F can't get us 0 anywhere.
So all we know is that on the boundary, let's add some color. On the boundary, here's the boundary of F, and here's the boundary of G. On the boundary.
Oh, it's only on the boundary. Okay,
only
sorry.
on the boundary.
Yeah, right. I was looking back at my notes. I was like, okay.
All I know, the interior goes
right.
like, and the interior goes like that, and they intersect somewhere.
Okay, makes sense.
If you have a single piece where they intersect, you could force a 0 there.
Yeah, of course. I just didn't write down the on the boundary part. So.
Yep. Yep. So this is crucial. Only on the boundary do I know that F and G. Whoops. I guess I can't erase just part of something. Only on the boundary do I know that F is strictly greater than G. Of course, if I knew it in the entire disk, it would be trivial. Yeah. But in fact, I'm proving it inside on the entire disk. Because if it wasn't true inside the disk, this would fail. Maybe that's an even better statement. Well, we're going to get an even better. We're working up to the maximum modulus principle. That's if it's not. So for those of you that have seen this before, that's exactly what the punchline will eventually be. But yeah, does that answer your question? Any other questions? Anna, something? No. Okay. So right. So continuity is equivalent to the pre-image of open sets being open, but of course, there's no reason for the forward image. Here we have a nice function. Let's go back to blue. Here we have a nice function. This is a nice, smooth function over R, and the image of the open set 1 to 3. I'm hitting every single point, including 2 and including 4. Is the closed interval 2 to 4. There's no reason that the image of an open set needs to be open. Okay, so no reason, even for analytic functions, for the image of open. So in other words, the forward, instead of F inverse of open, now I just write F of open to be open. There's no reason for this. So let me highlight here that there's an inverse, and here there isn't. Can't happen over complex numbers. Theorem, open mapping theorem. If F is holomorphic, then the image of an open set is open. In other words, whatever your region looks like, here's omega. Let me not draw across pages. Here's omega, whatever it is. If I take a little ball here around Z0, and I apply F, and I get some point, let's say W0, which is F of Z0, the image of this ball, whatever it looks like, it can't do this. It has to have a ball around W0. Okay? That's the statement. All right, let's see how we would prove this. In other words, it's kind of funny. It's the reverse of for all epsilon there exists a delta. So, i.e., what are we trying to say? For all z in omega, and for all delta bigger than 0, so for every little ball around Z0, there exists an epsilon positive. We're so used to for all epsilon there exists a delta, which of course is continuity. Now this funny thing that goes backwards. For all delta there exists an epsilon positive, such that for all W with W less than W0 is the image of F0, the image under F of Z0, for all W within epsilon of W0, there exists a Z near Z0 such that F of Z equals W. It's a complicated way of saying the image of an open set is open. So every single W, for every single W in an epsilon neighborhood, here's my W, in an epsilon neighborhood of W0, there exists some point in the pre-image in the domain that maps to it. i.e. W is in, i.e. The disk of radius epsilon about W0 is contained in the image of F. Does that make sense? Okay. All right, let's prove it. So let Z0 be given. Let Z0 be given. Set W0 to be F of Z0. And look at the function. Look at F of Z minus W0. It has a 0. This has a 0 at Z0. And, well, there's a neighborhood of Z0 where that's the only 0. F isn't constant. Yeah, by the way, this is not true if F is constant. The constant function does not map an open set to an open set because the constant, so. And F is not identically a constant. So this is essential, otherwise it's just not true. Okay. F has a 0 at 0. This is not the constant. This is not everywhere 0. So there exists a neighborhood, there exists a delta 0 such that for all Z minus Z0 less than delta 0, but not equal to Z0, F of Z minus W0 is not 0. In other words, I just want one value where I'm equal to W0. I want one value of F where I'm equal to W0, and all the other ones I'm not. Okay. So let delta be less than delta 0, but positive. Okay. Now, so you're giving me a delta. So here's my Z0. You've given me a delta, small enough that that's the only value of W0 in a neighborhood. And I want to know what happens under F. I get some value W0, and then I have some point W. So I have to give you, we've taken Z0, we've taken an arbitrary delta, small enough, we'll make it a little smaller if we need to, so that there exists statement. We could say for all delta small enough. So small enough means so that Z0 is the only 0. I have to specify an epsilon. Well, that's pretty easy. That's pretty easy. The region, how do I want to say this? C delta, or D delta of Z0, closure, is compact. And therefore, the image of F, so F of D delta Z0 bar, is also compact. Okay, I'm taking a compact region. Wherever I send it to, I don't know what it looks like, but it's also compact and therefore bounded. So for all, what am I trying to say? I just want to say there exists an epsilon. There exists an epsilon such that for all Z in this delta ball about Z0, F of Z minus F of Z0 minus W is at most epsilon. This is just continuity. I take some compact region, I apply a continuous function, I can't get super far away from the value. Okay, so there's a limit as to how far I can get. Sorry, that's not what I'm trying to say. That's not what I'm trying to say. That is not what I'm trying to say. Yeah. Sorry, I don't want this. What I want, I do want to use compactness, but I want it not to make something small. I want it to make something large. I want to make something large. Look at the boundary. Let's make this red. Look at the boundary. Look at the boundary of this disk. So C delta, which is the boundary of the disk of radius delta about Z0. And look at the image of that. F of C delta stays away from 0, doesn't equal 0, precisely because Z0, Z stays away from Z0 and is less than delta 0. Therefore, the function never vanishes. Which function? This function. I need to give this function a name. G of Z. I'm sorry. The function G of Z never vanishes. G of Z is the difference between F of Z and this W0. Every time you're away from Z0, this thing doesn't vanish. And on the boundary is a compact set. The image, wherever the image goes, let's see, where does the image go? It can't go like this. It can't get arbitrarily close to W0. Because this disk is compact. This boundary is compact. Therefore, there exists an epsilon such that absolute value of G of Z, so for all Z on this boundary, the absolute value is at least epsilon. In other words, this can't happen. This can't happen. What really has to happen is that I get some curve. What really has to happen is here's W0. The image of the red curve is some other curve. And that other curve does not get within epsilon of W0. Okay? This is a function on a compact set. It doesn't vanish. Therefore, it stays uniformly away from 0. Does everybody follow that? I know I gave you two versions of the argument. I don't want the whole disk. I just want the boundary. I can't say anything about the whole disk. The whole disk does get near Z0 and does get near 0. But the boundary of that disk stays away from W0, but uniformly. So that's the epsilon that I want to take. Okay, so that for every Z on this boundary, G stays away from 0. Of course, epsilon is positive. So far, so good? Again, what are we trying to do? We're trying to say, we're trying to prove the open mapping theorem. In a neighborhood of Z0, we get mapped to W0. I want to know that there's an open neighborhood. In other words, for every delta around Z0, there exists an epsilon around W0, so that for every W in this range, there exists a Z in this range, so that Z maps onto W from F. Make sense? Okay. What is IIE? IE? That's better. Okay. We got an arbitrary Z0, we got the image W0. We look at the function G, which is f of Z minus W0. It has a 0 at Z0, precisely by assumption, by what W0 is. And by shrinking, by zooming in, it never vanishes in the entire range. It never vanishes in the entire range except at Z0, means on the circle it doesn't vanish. And if I look at what the image of that circle is, that must stay some epsilon away from W0. So what? So what? Now let W be in this disk of radius epsilon around W0. Be arbitrary. Be arbitrary. Observe, here's a funny observation, G of Z, which was f of Z minus W0, is also equal to this. And I'm going to call this function big F, and I'm going to call this function big G. So it depends on W. W is fixed. Be arbitrary, fixed. Okay. What do we know on this, the boundary of on C delta? What do we know about the absolute value of F? W is inside this circle. Do you see? Sreeram, I lost you. Oh, you're muted.
Just trying to figure out.
Yeah. Again, so W minus W0, this is less than epsilon. G of Z is the constant function. It's not a function of Z, it's just a constant. And we're in a delta, this is less than epsilon. And how about this? The image f of Z on this boundary, well, that's this curve. Sorry. I'm sorry, that's not the function I want to take. So I want to make a new function. I'm sorry. I'm rushing through this argument. I want to make a new function, h, which is this function. I guess I need W0 minus W. Let's try this again. I'm making a new function. W is fixed. W is given. I make a new function. So let h of Z, which is f of Z minus W0 plus W0 minus W, be a new function. By the way, what is this function? The W0s cancel out, and I get f of Z minus W. What do we know about f of Z minus W0 on the boundary? That's the red curve. It's at least epsilon. What do we know about W minus, so the absolute value of W minus W0?
It's less than epsilon.
Strictly less than epsilon. Yep. Therefore, the absolute value of f is strictly bigger than the absolute value of g on the boundary. What does Rouche's theorem say? Inside this disk of radius epsilon about Z0 is equal to the number of zeros of f plus g inside this boundary, inside the same region. Does that make sense? This was our original function, g, little g. I screwed this up a little bit. This was our little function, little g. I'm trying to improvise these proofs so that you get the feel for, you don't always get it right the first time. And here we are. This is f of z minus w0. Now, what do I know about how many zeros there are of big F inside this region? Yeah, it's exactly 1. Therefore, f plus g has exactly 1, 0. But what is f plus g? Big F plus g is h, which is f of z minus w. Has a 0. Implies big F plus g, which is little f of z minus this fixed point w, has a 0. In fact, it has a unique 0. But never mind. Therefore, there exists a z in that disk so that f of z is equal to w. In other words, w is in the image. So we used Rouche. We used Rouche to show, we used Rouche here to show that an arbitrary point w, I guess it's up here, here, an arbitrary point w is in the image. Rishabh, did you want to ask something?
Yes, Professor. So can you go to this page where you used compactness?
Yes. So that was right here.
Yes. How exactly? What definition of compactness did we use? Like absolute value of g of c greater than or equal to epsilon. So.
Okay, so c sub delta is this circle. If you take limit point on the circle, it's on the circle.
Okay.
So it's closed and it's bound.
Okay.
Which is equivalent to if there's an open cover, then there's a finite subcover.
Okay.
Okay. And the fact that g is now, okay, you can think about the function. You're asking about this. Why does there exist an epsilon, right? So you can think about the function that sends a point on the circle to the absolute value of g. Whatever that looks like, it's a function on a compact set, so it achieves a minimum.
Okay.
And it's never 0, so the minimum is never 0. That's the existence of this epsilon. Does that make sense? So there's two functions. There's a function little g, which was f of z minus, which I later called big F, but so be it, which is f minus w0. And then there's another function h, which is f of z minus w. And what we're showing is that the first function, f of z minus w0, has the same number of roots as f of z minus w. But the former has a root, therefore the latter has a root. By Rouche. Thomas, something you don't like.
How do we know?
Well, I need to see your guys' facial expressions. I can tell if you're, yeah, go on.
How do we know that the inside of the compact set we started with stays on the inside of the image, or do we not need that? Does that not matter? We
don't know. Yeah, we don't know anything about that, the structure of that. So all I'm saying is, you're asking again about this part?
No, I'm just asking, how do we know like the interior doesn't like spill over? I'm asking more like on applying Rouche. Like, how do we know that the 0 is in the interior?
So, well, we know it's not on the boundary. No, I'm not following. Rouche says you have a disk, and you know that on the disk, some f in absolute value exceeds strictly some g in absolute value. Then the number of zeros inside the disk, and
oh, I see. I think I got confused with the pictures as to which one we were using as our domain. Okay, no, yeah, that makes sense.
This is our domain. The disk is our domain.
Right.
And the boundary of that disk is this C. And then on this boundary, f by construction is at least epsilon, And G by construction, it's just a constant, it's not a function of Z, is strictly less than epsilon. And therefore F is strictly bigger than G. So they have the same number of zeros. This one has a 0 exactly at W0. This one also has a 0, which is, by the way, unique, which is a slightly stronger theorem. It's locally one-to-one. Not only is it locally open, it's also locally one-to-one. Yeah, let's remark the proof shows that F is locally one-to-one. Okay. There's something I don't like about this. All right, let me come back to it. There's something I don't like about this. Should I tell you what I don't like? If it'll take us on a little excursion.
If it's locally one-to-one and you restrict its image, it will become biholomorphic, right?
Yeah, I don't like that. I don't like that. Here's what's wrong.
Need not be.
Okay, good. I see what's wrong. Let me tell you yeah, so this can't be right. This can't be right. Let me show you what's wrong. Non-example. F of Z is Z squared. Is right here. This is what's wrong. I didn't say Z0 was a simple 0. If this has multiplicity, this might have lots of, if this has multiplicity too, this deformation might distinguish what used to be a double 0 and is now, yeah. So the non-example, it's an easy non-example in a neighborhood of, if you look at what's going on, I'm going to try to do my best at this drawing. Z goes to Z squared. What it'll do is it'll wrap, like I have R e to the I theta, that's going to go to R squared e to the 2I theta. And so that's going to wrap around twice. Instead of theta wrapping around once, theta will now wrap around twice. So it's absolutely not locally one-to-one. Okay, and the mistake was right here. It's not equal to 1. Z0 need not be simple. Need not be simple. Well, it is one-to-one if and only if. No, not necessarily if and only if. So if this is more than 1, then there's a 0, but there might be more than 1 0. That's all. So there is a remark. Proof shows that if Z0 is a simple 0, of G of Z, which was defined to be F of Z minus W0. In other words, if I don't hit W0 with multiplicity, in the sense of F of Z minus W0 having a multiple 0, then locally F is one-to-one. So it fails to be one-to-one if and only if its value at W0 is hit with multiplicity.
Near Z0, you mean?
But then it's locally locally near Z0, F is one-to-one. Locally near Z0. Okay? Good. I'm glad we got that sorted out. So I knew this couldn't be right because of this example, because of what happens to the squaring map, which we will discuss in detail very soon when we start talking about complex logs. So that's what was wrong with this. This we did not assume. There could be the number of zeros counted with multiplicity. Z0 is the only zero, but it might have multiplicity, and then we have no idea what happens to that multiplicity. It need not be preserved, that it need not be the case that there's only one Z. Okay, any questions? Sorry, this took a little longer. This is a good time for a break. So the question was, where does the proof fail? Where does the proof fail over R? So it fails in a number of places, but most notably, it fails on Rouche itself. Maybe I should have pointed that out for Rouche. Here's a function. Here's a nice region, disk. The boundary of the disk is 2 points, is A and B. Here's A and here's B. And you can absolutely have a function f that's above G and a function G and absolute value of f is strictly greater than absolute value of G on the boundary, meaning at these 2 points. And yet their values cross in between. So you might say, okay, let's circle back. Where does Rouche fail? Right?
Real quick,
Please.
why are you saying they cross? Because I thought we were talking about the zeros of f plus
Yes.
G.
So in other words,
Wouldn't that be f minus G is 0?
yeah, so replace this is really the graph of minus G, if you like.
Oh, okay, I see. Right, and we're just absolute valuing it.
Yep. The only question is about the absolute value. So there's nothing wrong with this for analytic functions on the reals. Where does Rouche fail? Let's go back. So that's a crucial input to the open mapping theorem. Where does Rouche fail?
The argument principle is not true.
Well, so we've made this assumption. So yeah, first of all, there's the argument principle. Well, if you take f prime over f and you integrate it, that is d log. So you get the value of log f at the 2 endpoints, the difference of log f at the 2 endpoints. That's not in general, I mean, there's no residue calculus. And so there's no reason for that to be equal to an integer. And in particular, this is where we were using the fact that this is an integer. It's the continuity. It's this f sub t being integer valued. Okay, so let's make that remark so that we really understand these proofs. Where does Rouche fail? Does proof of Rouche fail? So if I integrate, well, it already fails at the integral of the boundary of a disk of f prime over f. That just means evaluate, right? The boundary of the disk is 2 points. So it's f prime over f of b minus f prime over f at a, and there's no reason for this to be an integer in general. And we crucially used the fact that this deformed function f sub t is continuous in t and integer valued.
Do you mean log f at b minus?
No, because the boundary, to integrate over the boundary means
Okay.
to take this function and add it at the 2 boundary points, right? As a still just integral. There's a delta spike at b and a delta spike at a with orientation that gives you a minus the value. So it's the z-valued, it's the z-value thing that's wrong. In particular, it goes all the way back, if you like. Rouche fails because the argument principle. There's no argument. There's no theta. So it fails because the argument principle fails. No argument principle.
So what is the equivalences among all these theorems, like maximum modulus, argument principle, Rouche's theorem? Which one is stronger and which are equivalent?
Gosh, they're all true. And so they're all equivalent tautologically, but that's not what you mean. We're deriving them in this order, which is also the order of the book, if I recall, from the argument principle, which is like the easiest thing to prove. Rouche is a one-line corollary. The open mapping theorem is a corollary. The maximum modulus principle, which is I'm about to state immediately, is an obvious corollary. Could you prove the maximum modulus principle directly and then from it derive the argument principle and Rouche with some other arguments? I would bet you could. This is just they're all true. So it depends on what how much arguing you allow. All right, so let's prove the maximum, so theorem, maximum modulus principle. Again, I need F to be non-constant, F holomorphic, and non-constant on some region, omega. Then what? Maximum modulus principle. F is holomorphic and non-constant on a region. And I want to assume that F is continuous on the boundary. So I want to have an extension to the boundary so I can speak of the boundary. Then the maximum value, the supremum of absolute value of F on this open region, omega, is at most the supremum over the boundary. In other words, for Z in the closure, take away omega itself of the absolute value of F. Okay, so I have some region omega, I have some function. Let me draw a picture. So here's omega. Here's the graph of F, whatever it is, it's some surface. It cannot happen. Let me try to draw the boundary. So here's its value on the boundary. This cannot happen. The supremal value, come on, this does not exist. The supremum value of F must happen on the boundary.
Is this also true for like omega, like the upper half plane, or do we need some sort of like boundedness?
We will get to, so it's definitely not true. Where did I say? And bounded. Thank you. And bounded. Yes, it is essential that you put here that omega is bounded because it's not true. Okay, let me make the remark now. I was going to save it for later. Remark, it's essential that omega is bounded. There's an easy counterexample. E to the z squared. So let's look at this region. Let's look at e to the z squared. If z is here on this 45-degree angle, so this is e to the pi I over 2 times r, or on this side, so this is plus or minus. Sorry, I want the plus or minus inside the exponential. Plus or minus pi I. Okay, so this is up 45 degrees or down 45 degrees. Then z squared, the reason I want that is because z squared will come out to plus or minus I times r. Because now I get e to the pi I. over 4, I'm sorry. You know, you have good days, and then there are other days. Pi I over 4, I want the 45-degree angle. So that when I double it, I get I or negative I. Then the absolute value of e to the z squared is equal to 1, because it's an imaginary, purely imaginary number. And yet, if this was my region omega, obviously I do not stay bounded. This blows up, because it's e to the x squared. Okay? So it is essential that omega be bounded, but there will be something called the Fragment Lindelof principle that we will see later. Later, we will see the Fragment Lindelof. Principle that says, as long as you don't blow up this fast, then there's a version of, then actually you have, then what's on the boundary determines what's on the interior. So the Fragment Lindelof principle, let me state it loosely, as long as you don't blow up too fast, the behavior on the boundary determines behavior inside. Okay, just planting that seed. So again, we will crucially use that omega is bounded, f is holomorphic and non-constant, and assume f is continuous to the boundary so I can look at the supremum on the boundary. This is just to, there's no reason that f has to have continuation to the boundary, but if it does, then the largest value is on the boundary.
So the statement you have written doesn't prevent another largest value from being inside also, right?
Whatever the largest value is on any region, it has to happen on the boundary of that region.
It could happen on the boundary as well as inside also. Maybe that's prevented by something else. But
if it happens inside, then zoom in on the inside. And it has to happen on the boundary everywhere.
what?
So you're saying, okay, so you're saying what could the supremum value, max value, happen both on the inside and on the boundary. Okay, so the hypothetical situation is, here's my region omega, here's my boundary curve, which has a maximum, but the inside part also reaches that same maximum. Okay, so these are at the same height, two maxes. Okay, so here's what I'm going to do. I'm going to take a slightly smaller region.
Okay.
Around where your interior maximum was. Then a smaller region around interior maximum. In fact, any smaller region around this interior maximum needs to have the same maximum. And so you would have an entire limit, you'd have an entire ridge. And if you have a ridge, then the thing is constant. So that certainly can happen if the function is constant. Then the smaller region around the interior maximum also has max on its boundary. Okay, so the maximum cannot be in the interior. All right. Good. So what do I want to say? Oh, I have to give the proof. So, proof. Assume there exists, here's another way of saying it. Assume there exists a point inside omega such that for all other points, z0, for all other points in omega, f of z is bounded by f of z0. Here's another way of saying the same thing. You don't have to think about the boundary if you don't want to. If there's a point that is a maximum, then, so here's z0, and here's the map f, and here's f of z0. So here's the ball of that radius. All of the other values have to be inside that ball. Because in absolute value, they don't go past that ball. And what's wrong with that?
Violates the open mapping.
Open mapping theorem. Violates open mapping theorem. Violates open mapping theorem and implies f. The way that it violates the open mapping theorem is that it implies f is constant. So it can happen. It certainly can happen that there's a maximum on the interior, but if there's a maximum on the interior, then the function is constant. Did I say the function has to be non-constant? Yeah. I don't have to say that it's non-constant, actually. It's true. If it's constant, it's not vacuously true, but it's trivially true. Okay? If it's constant, then it's fine. And if it's non-constant, then the open mapping theorem says this can't happen. I need a ball around f of z0. Make sense? All right. What else can we do? Okay, homotopy. We're on to homotopy. Yeah, let's just get started. Any questions? Any questions? We're working our way up to complex log. We're very close to it. We've seen Rouche's theorem, the argument principle, the open mapping theorem, and now the maximum modulus principle. Okay, let's do it. Homotopy. This is really a topological question, but as you'll see, complex analysis forces on you various topological questions. All right, so two curves. So two curves, gamma 0, let's say from 0, 1. I'm going to now conflate the curve and its parametrization to some region omega, and gamma 1 from, let's say, 0, 1 to omega are said to be homotopic. They're homotopic if there exists a homotopy. If there exists a curve gamma from 0, 1 cross 0, 1. So I'm thinking of gamma as a parameter. So this is an S parameter and this is a T parameter. So I write it as gamma sub S of T. And I didn't say the main thing with gamma 0 of 0 equal to gamma 1 of 0 and gamma 0 at 1 equal to gamma 1 at 1. In other words, I want them to start and end at the same point. Let me draw a picture. Here's omega. Here's some point alpha. Here's some point beta. Here's a curve gamma 0. Here's a curve gamma 1. So they start at alpha. They both end at beta. They're both inside this region omega. And two curves are homotopic if there exists a homotopy. So this thing is called a homotopy. This function. So that, so I'm thinking of gamma S being a curve. So this is a curve. So let's see. Let's say gamma S of 0 equal to alpha, gamma S of 1 equal to beta. So again, all of these curves have the same starting and end points. And this homotopy is jointly continuous. Jointly continuous in S and T. Okay? So the pre-image of an open region, you know what I mean. The pre-image of an open region is an open region. So we're thinking of now S and T being 0, 1 to 0, 1, being mapped to omega, whatever omega is. And if I have a very small region here, so small open region here, the pre-image under, this is gamma inverse, is some small region of S and T. If I wiggle S and T just a little bit, I'll get values that wiggle just a little bit. Jointly continuous. Okay, and what I want to say is a theorem that will take a little bit of work. So maybe we won't do it today. I'll state it. And maybe that'll be a good place to stop. So here's the theorem. It's kind of a, in some sense, obvious that we should be able to state something like this, and we should have been able to state it some time ago. But F is holomorphic. F is holomorphic on omega, and we have two curves, gamma 0 and gamma 1 are homotopic curves. Curves in omega, then the integral over gamma 0 of f of z dz is equal to the integral over gamma 1 of f of z dz. Okay, so if you haven't seen this before, what's not homotopic? If omega looks like this, and then I have two curves from here to here, and then another curve from here to here. At the moment, we don't yet know how to prove that they're not homotopic, but intuitively it should be clear that there's no way to continually deform one to the other. And pretty soon we'll have all the tools we need to prove things like this using complex analysis. So yeah, maybe that's a good place to stop for today. Any questions?